dot structures for atoms that can break the octet rule. So let's start out with, for example, group 3A, okay? Leading with boron, right? So let's do something like BF3 right here, okay? So what do we have? 1 boron and how many valence electrons? We have 3 valence electrons because it's in group 3A, plus 3 fluorines at 7 valence electrons each. So 21 plus 3, guys, is 24 valence electrons. The central atom here is going to be, let me write with something else that seems to be not right. Okay, so the central atom is going to be B. Okay, and then we're going to make 3 connections, F, 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 right? And we've used 6 electrons, so we have 18 electrons left. And so we start to fill outside ones, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So we've used 18 electrons, and we got nothing left, okay? So typically, this is the part that you would ask yourself, is everybody happy here, okay? And you'd be very tempted to say no, because boron wants to have a full octet. But, guys, boron is actually just fine with having 6 valence electrons, right? But let me tell you something, that here, even if you wanted to, okay, let's go back and talk about that later. But we can't really do double bonds on this. I'll explain why later, even if you wanted to. But we know that boron is in group 3A. So when you do the Lewis structure for this, you do 1, 2, 3, right? So remember, boron, in that case, has only got 3 electrons to share, because covalent bonding is all about sharing electrons, not giving them away. What? So it means in order for boron to make a bond with something else, I have 1 electron, you bring in another electron, and we form a bond that way, right? So it's only got 3 electrons to share, so we'll only form 3 bonds here. This is an empty orbital, right? And unless something is generous enough to share 2 electrons with boron, it's only going to be doing 3 bonds. And that 3 bonds means it's happy here. It means we don't need to even put lone pairs on this. So anyway, we won't be able to put it on there because we ran out of electrons. So boron is happy because it's in group 3A, and all other elements in group 3A, aluminum, when it forms covalent bonds, it's going to be just fine with 3 bonds, not 4. 6 valence or 6 electrons, not 8. Okay? So boron and any of the other group 3A elements will only have 6 valence electrons around them. Okay? Now, let's talk about another exception. And another exception is group 3A, or pardon, 2A. Now, you may say to me, wait, group 2A is made up of metals. So metals don't even form covalent bonding in molecular compounds. But remember, guys, that idea of ionic or molecular, right? It's not so black and white. It's more of a spectrum. So some elements like aluminum and beryllium, for example, is the one that I want to do next, can both form covalent bonds and ionic bonds. So when we're talking about BeCl2 here, okay, let's do an example of how to do the Lewis structure of that. We have 1 beryllium, and beryllium is in group 2A, so it has 2 valence electrons, plus 2 chlorines at 7 valence electrons each. So 14 plus 2, that's 16 valence electrons, yes? Beryllium is going to go in the middle, and we're going to make 2 connections to chlorine. We used 4, so we have 12 left over. So we're going to fill in outside. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And when we did that, that's 12, and we got nothing left over. So hey, that's good. But again, you're going to be tempted to say, well, beryllium is not happy. But it actually is, because beryllium has got 2 valence electrons only. So remember, if you have 2 valence electrons to share, you're likely going to form only 2 bonds. So that's where that 2 bonds come in from the chlorine. And you will be just fine with that. And we observe this compound readily. Now, of course, beryllium can also form, and group 2A, they can also form ionic compounds. But that's a different story. So watch out for group 2A and group 3A. Now, the next thing that I want to talk about, with exceptions to the octet rule, is now we're talking about period 3 and below. Remember, period means row on the periodic table. So row 3 or below. What do you guys know about row 3 elements? So let me remind you a little bit, if you haven't done valence shell, or pardon, electron configuration. N3 is the 3rd shell, right? So that's where the 3rd period is, right? We have S, P, and D electrons. So here, guys, we have S and P. Remember, these can fit 2, this can fit 6, and this can fit 10 electrons. So look, when we fill S and P electrons, that's where the octet rule comes from. But guess what? In period 3, we also have D orbitals. So we literally have more space or more apartments to put electrons in. And so elements that are in row 3 and below on the periodic table, so period 3, 4, 5, 6, and 7, can and will break the octet rule. So let's do an example of such case. Let's do SF6, okay? SF6. So look at sulfur, okay? That's the central atom here, right? Sulfur is in group 6A, right? It's in period 3. So can it break the octet rule? Absolutely, because it's in period 3 or below, it can break the octet rule, or just period 3 in that case, right? So 1 sulfur, okay? And it's got 6 valence electrons because it's in group 6A, plus 6 fluorines that, and remember, fluorine is in group 7A, so that's got 7 valence electrons. So guys, 6 times 7 is 42, plus 6 is 48 electrons to share between these guys. So sulfur is gonna go in the middle, okay? Then I'm gonna go ahead and make 6 connections to fit in my fluorines. 1, 2, 3, 4, 5, 6, okay? Now look at what I did. 1, 2, 3, 4, 5, 6, 6 times 2, that's 12 electrons, right? And so I have 36 electrons left. And I know I have 6 outside electrons, right? So each of them needs 6 more. So 6 times 6 is 36. And so I've used everything up here. Notice I got nothing left now. But I'm good. Now, again, look at sulfur. Because it's in period 3, it can do more than the octet rule. It can do more than 4 bonds. It's doing actually 6 bonds, 12 electrons. Again, because it's got those empty d orbitals. Now it has space to put in more electrons, okay? And so that's why earlier, when I was talking about BF3, let me tell you something. BF3, or fluorine. Can fluorine ever break the octet rule? You've got to ask yourself, is it in period 3, row 3 or below? No. Fluorine is in row 2, okay? Which means fluorine can never, ever break the octet rule. Fluorine will always have 1 bond, right? Because it's already got 7 valence electrons, and it likes to do 1 bond to get its full octet. So you will never see fluorine, just like hydrogen as the central atom, you'll never see it form double or triple bonds or any of that, because it's in period 2. Now, same thing, carbon, nitrogen, oxygen, right? Those guys do not break the octet rule. They literally cannot fit any more electrons because they only have s and p orbitals, no d orbitals. So there's no place to put extra electrons from additional bonds, okay? So let's do another example and ask ourselves something. We have SeF4, okay? And so, selenium, guys, is in group what? It is in group 6A, right under sulfur, right? So we have 1 at 6 valence electrons, plus 4 fluorines at 7 valence electrons, 28 plus 6 is 34 electrons, okay? So now, you want to put selenium as your central atom. How many connections must you make here? You need 4 connections. So 1, 2, 3, 4, right? Fluorine, 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 fluorine. So you use 8, which means you have 26 electrons left. Each of these outside, because remember, fill in outside first. Each of these needs 6. And 6 times 4 is 24. We erase, or we subtract that from here. We got 2 electrons left. Since we got extra electrons, where did those go? On the central atom. And again, that's sound, and it's good, because selenium, guys, is in period 4. And so it can and will break the octet rule because it's got additional d orbitals to put these extra electrons in. So look, 2, 4, 6, 8, 10 electrons surrounding selenium. That's all right, okay, because it's got d electrons. All right, that sums it up for how to do Lewis dot structures, taking into account exceptions to the octet rule.